Cool. All right, can you guys hear me? Cool. All right, so, I'm Chris Ellis, or sometimes I'm Chris Join Engine, or Join Engine, or Joiner, or a number of variants on that, right? But I'm kind of here today to talk about genetic algorithms. So what that is it's kind of a simple to implement machine learning algorithm, which is it's kind of fun and kind of cool and a little easier to understand. And then I built a proof of concept tool around this that can brute force some websites, right? So I'll show you guys that. And let me just cut to the chase, because here's the moment you guys are all waiting for, and I'll spoil it here. It actually works, and in some situations it can work pretty darn well. So kind of what I'll talk to today is give you guys a quick overview of what this looks like, what this tool is. Then what is a genetic algorithm? So what exactly is it? How can you implement one of these things if you want to kind of build it into some offensive tooling yourself? And then how does this compare to traditional methods, right? So why would you use this thing over kind of a statistical analysis approach or some kind of heuristics or something like that? And then, the scary part for me, because nothing ever goes right when you do a demo, but I'm going to try to give you guys a demo. And then just real quick, I'll touch on some other machine learning applications kind of in offensive security. Because why do these defensive guys get to have all the fun tinkering with that stuff, right? So who am I? And to that, I say nobody really cares, so I'll just skip that. But I do have to give one quick disclaimer. So I do work for Kaiser Permanente, which is a healthcare company back in the United States. And they have some lawyers, and those lawyers advised me to say that, this is kind of my own brainchild, and that, any views I express here do not necessarily represent the company. But that being said, this is kind of our first foray into releasing some stuff to the public. So if this goes well and I don't piss too many people off, then you may see some more of our stuff down the road kind of in the future. I know some of my coworkers have some cool stuff around reverse engineering that'll be exciting to see. Okay, so let me just start off with an anecdote, right? So I have a customer come to me, and they basically have some new web service they're trying out. And they say, okay, we give every customer some kind of URL or some kind of token, and it's like 6 or 7 or 8 digits. And anybody who presents this URL token can access some kind of web resource, so some of their personal information. So we give this user a URL. Anytime they present this URL, they can see, their information. And they say, well, do you think this is secure? Which is kind of a loaded question, right? So I'm kind of looking at this thing, and I say, well, the entropy is pretty good, right? If I want to get into Chris's personal information, I'm not going to be able to do that because it's long enough and it's random enough. If I want to get into John's or Bob's personal information, I'm probably not going to be able to do that. But I'm kind of a jerk, right? So I say, well, this customer has millions of clients of their own, and, so the space is saturated enough, maybe I can actually get into some people's spaces, right? So I decided to build a brute forcer to kind of see how far I can take this. And so I'm kind of analyzing these tokens, and I'm looking at them and I'm saying, well, they didn't do this right. And by that I mean these tokens don't look entirely random. They have, more lowercase letters than uppercase letters. They have more numbers than, lowercase letters and all these things. And there can be variable lengths, but the variable lengths, certain lengths seem to pop up more often. And me wanting to build a good brute forcing tool so I can get a good kick out of this, I go through and I kind of start doing some statistical analysis, and I start weighting my tool so it has different guesses. And I say, I'm too lazy to do this, forget it. So instead I kind of implement a machine learning algorithm to do it for me. So that's kind of GA Forcer. And I named it GA Forcer because I'm original and creative, then no. That's the best name I could come up with, right? And just kind of a sample run here. You guys can kind of see it. And it looks kind of confusing, but I'll explain it real quick. On the left is kind of the first run on the program. And what this matrix is it's got a bunch of different threads running. And each thread is taking a different approach to brute forcing, right? And this one's guessing, 47% chance of a lowercase character, 50% chance of an upper, 2% of a digit, and then kind of min and max lengths, right? And it's all over the board at first, and then kind of after 11 iterations, you can see it went from guessing 19% to guessing 48% correct. And you can also see that it's kind of zeroed in on kind of an optimum solution for this particular problem space. And those of you guys who are staring at this thing, you're going, what the hell? I'm seeing some kind of sideways vectors here with the similar weights but different scores. That's because this particular target, I just kind of wanted to throw something up on the screen, and this particular target had like an IPS or an IDS or something. Hypothetical target, right, had an IPS or IDS, and it was blocking me along the way a little bit. And I didn't run each thread very much. I think I did like 15 runs, so maybe not statistically significant, but just kind of show you an example of what this thing kind of looks like. So maybe kind of taking a step back, right? What actually is a genetic algorithm? How could you build one, right? So just kind of by way of a quick summary, all it is it's just a tool that takes a set of guesses and then kind of refines them over time to, make better guesses. And, a lot of these machine learning algorithms kind of take this notion of mimicking something in nature, like, your brain or something like that. And genetic algorithms are very similar in that they mimic this kind of notion of evolution or kind of, progressive improvement, survival of the fittest. And each member of this kind of initial population that we have has a chance to survive and move on and then kind of mix and match genes with other well-performing threads and, get better as it goes and goes and goes. And what's really cool about this, and I'll talk specifically about this, and it actually has some really cool traits when you look at password cracking, is the end result of this algorithm is it becomes super robust. So you can kind of throw all sorts of curveballs at this thing, and it does some kind of cool stuff, right? But so, you start with this population, which if you're looking at kind of a brute forcing tool could just be a set of threads, right? And they have some goal, so attacking a web server or something like that. And then from there, kind of how do we determine what moves on to the next generation? And how do we mix and match some kind of traits of these positive performing brute forcing threads, right? And the magic kind of comes down to, well, we fire them off, we look how they do, and then we pass them to something which is called a fitness function, which basically just measures how well they did, right? And then we kind of apply three fundamental, cornerstones of genetic algorithms, which are just roulette-style selection, crossover, and mutation. And we kind of go in that order. And what these are is roulette selection. Each thread gets kind of a piece of a wheel, and depending on how well it did, it gets a bigger piece or a smaller piece, and we just spin the wheel a bunch of times. So think, random weighted selection. And it's kind of important to note here that things that didn't do very well can still move on to the next generation. Things that did very well may not move on. Sometimes things can move on, multiple times. And if you kind of take it back to this example of in nature, right, survival of the fittest, this is kind of analogous to some hardship or some disease or starvation, and the more fit threads get to move on, right? Then we undergo this thing called crossover, and it's difficult to explain, so you guys get to look at some of my lovely programmer art here. But basically what this is we try to take traits from well-performing threads and mix them. So we kind of pick a random point in our parameter set of each thread, so just the weights it's guessing, and we just cross them over. So kind of here, if you had a thread that, is represented by a straight line and a thread that is represented by a squiggly line, and these are two kind of well-performing, threads, these guys get matched up for crossover, and then you have one thread that's a straight line with some squiggles and one that's a squiggle line with some straight lines, right? And, this has an analogy kind of in the animal world too, and I'll let you guys figure that one out on your own, right? But then finally we've got mutation, which is pretty much exactly what it sounds like. So we take all these well-performing threads that have kind of been mixed up and matched up, and then we just kind of roll the dice for each parameter with a very small chance, and we can adjust the parameter any which way we want, right? And we have to keep it a small chance, because if you don't, you end up with a kind of random search algorithm, which is just a brute force. So just kind of touch it up a little bit. This is kind of the problem space in my head. And you can see here you've got a bunch of hills and valleys and things. And the way I look at this is you've got some, shorter hills, which are kind of good solutions or local maximums. And then you've got like one big hill over there, which is a great solution, right? So the global maximum. And that's kind of where you want to end up on. And kind of the classical conventional approach to a problem like this is you kind of pick a point and you move in the steepest direction nearby. And as long as you're improving, you keep moving in that direction, right? So if you don't like the hill algorithm, this is kind of like you're going to a target number and you just kind of increment to get there kind of thing. But that has some problems, right? So if you started out here in this valley and you go, oh, there's a steep slope this way, I'll go here, you get stuck up here, right? And so it kind of runs into problems when you have a space like this with lots of different problems, lots of maximums, right? You can also get screwed up if you kind of run into this situation where you don't have necessarily kind of a smooth graph, right? You've got bumps and squiggles and all sorts of things, or breakpoints. And kind of, there are conventional approaches to kind of overcoming this too. But the way a genetic algorithm does is you kind of start out with a population of points, right? So we talked about that with multiple threads. It kind of shifts towards correct directions. And then you've got this mutation thrown in with a very small chance, so that even if you do get stuck up here on this little teeny dinky mountain, maybe you have a random kind of input and it pops over there, and all the threads just kind of start evolving in that direction because they see that it's performing better. So that's kind of some of this robustness just intuitively for you. That's kind of cool. And now you guys are probably sick of that. So let's talk about how this tool actually works, right? And before I had the creative name of Genetic Algorithm Forcer, I was calling it Link Forcer, right? Even more creative. So it's a little old screenshot, but I've kind of alluded to it already. But basically what it does is I leverage a genetic algorithm. So I kind of start off with a pool of threads, and they all go off and try to brute force something. And they do it for some kind of set number of iterations, and it's fully configurable. And then you kind of look at the web response, which is like a 302 or a 200 or something like that, and you say, okay, I have a hit here, right? So that's a success. And then you kind of pump to this fitness function, which is just basically a way of saying, how well did I perform? And then you go through these 3 tenets of genetic algorithm: roulette selection, crossover and mutation. Your new population is ready, and then it fires off, right? And the process repeats. So kind of pictured here is just a run, and it's just going through one quick generation. And in this particular case, I was targeting one of these URL shortening tools, not necessarily because it's a good example, but because it's hilarious to kind of hit these things, right? And kind of on the right, I had to censor it for certain reasons, but was the guesses it was making. And then on the left here is kind of the output of what it's actually visiting, right? So it says, oh, I found a 302, that's a hit. Let me pipe it to the output, right? And now here's where things get kind of interesting. You're probably saying, well, Chris, how well does something like this work in the wild? Is this something that I could leverage? And even if you aren't asking that, I've got the answer, right? So it works pretty good, right? But before I kind of jump in, there's a couple of caveats. So my test target is kind of a database of passwords, right? So I went out and I searched for plain text passwords, and basically did that until I was bored of searching for plain text passwords, and that number seems to be 44 million. So think like, LinkedIn, RockU, eHarmony cracks, those kind of things, and I just shoved them into a database. And then I kind of set up a web server, and you guys will see it in a second when I demo this thing. And basically all that web server does is queries the database. It returns a 200 response if you get a hit. It returns a 404 if you get a miss. And it's, kind of akin to password cracking in that sense. So you make a password guess, you get a hit back, or kind of the example I talked about earlier where some vendor or something has some token in a URL and you're trying to guess it. And it's a little limited that I don't actually bother taking out entries when you get a hit. So that's kind of a little caveat here. And I only guessed length 6, and that's just because brute forcing has a lot of empty space, and I'm impatient and didn't want to have to run 10 million tries to have statistic significance, right? But I took kind of 4 approaches. So I did kind of the raw brute force, right? And this is somebody who doesn't know what they're doing, just throws something up there. It may not be proportionally correct. So if I took my character set as digits and letters, I give 50% chance of picking each one, which is not necessarily mathematically correct, but did it anyways. And 10,000 guesses, I had like 3 hits, right? It's just garbage. Nobody's going to do that. So then I did it a little bit more correct, and I kind of lined up all of my character sets and picked from a random spot in the line, which is maybe a little bit more mathematically correct. And I get like 7 hits. So then I say, okay, well, let's do this the right way. And I take 1 million passwords out of my database. And I start looking at them and I say, okay, these are composed of all these things. And they're all length 6. And if anybody's curious, for length 6 passwords, it's pretty much majority lowercase and then some numbers and very few uppercase. And I hope, you know, nobody's using like 6 passwords to protect anything on the internet, just saying. But, you know, I did this and I got 23 hits. And so now we're kind of getting to the acceptable range. And depending on what you're doing, if you're kind of doing an offline attack, right, this is reasonable. I didn't take it as far as I could have, right? I could have done these things where you pair up characters and you say, U's come after Q's and all that fancy stuff. But like I said, I'm kind of lazy. And then I fired off my genetic algorithm brute forcer, and to my great surprise, I had like 80 hits. And that kind of surprised me, right? And until I realized what it was doing. And you guys will actually see in a second kind of what it's doing. And it's actually kind of cool. Basically, it zeroed in on a pattern that I guess I should have seen coming, but it's kind of an interesting notion. Real quick, if I take off this length 6 restriction, and what does this graph look like? And this is, just take it with a grain of salt. It looks something like this, right? So now my genetic algorithm has 2,600 hits. And basically what it did was it zeroed in on shorter passwords, right? So threads with, it's easier to guess shorter passwords. It zeroed in real quick on that and started guessing shorter passwords. But I just kind of love this graph because it's like, what? I mean, you can't even see these first two, and then, you know, you can kind of see statistical base, looks like a blurred line kind of thing, and then you've got this massive one. But, you know, a couple caveats. I didn't do this for the other methods. This is just like the graph from before compared, and that's because it's difficult to do traditional brute force with variable methods. It just is, at least in a way that makes sense to me. And, you know, so it figured out what's shorter. You know, this is kind of the strength of something like this. And to kind of quote a teammate who's a little bit smarter than I am, if you know there's a pattern there, but you're not necessarily sure what to look for, this is a pretty decent approach. And so now let me give you guys a quick demo. And this is kind of the scary thing because I don't know exactly what it's going to do, but I have a good idea. I've run this like 100 times, and 95% of the time it does what I want it to, and then 5% it's like, oh shit, okay. But we'll see here. So here's my database, right? And I just throw in shit in the URL. And if it's in the password or it's in the password dictionary or whatever, my database full of real people's passwords, you get a nice 200 response. Not in the database, Bob. 404, because nobody's using that as a password, right? And I'll throw that in my actual password dictionary, so don't use that as a password now, right? But, and, you know, back to 200s. So that's it. It's, you know, real simple. And here's a nice command prompt. And the first one's just my database running. All right, so this is kind of the tool. And, it, you know, as it goes, it generates these 3 files. And I'll talk about those in a second, but let me just go ahead and get rid of those. So you can see there's nothing up my sleeve here. Java-jar. And I wrote it in Java. I know everybody loves Python, but this is like blasphemy, but I don't like Python, so I write a lot of things in Java. So this is kind of what the tool looks like, and I was trying to use somebody else's tool recently and found out that the documentation was really ugly. So I kind of make these fancy command line things here, right? But you've got some options, which is just kind of S, which is the size of your generation, how many threads, I, which is how many iterations per thread. So what do you kind of measure success by? Zoom? Oh. Yeah, let's see if I can figure out how to do that on this thing. Bigger. View. Bigger. Is that zooming at all? Yeah, if it's something like that, just scream at me, right? Because I don't know where I am even, man. So, but, okay. So we've got some flags here, right? S is kind of the size of the generation. So how many of these threads you're spinning up. I is, you know, kind of the number of tries per generation. And you got some things here. Min and max length, that's kind of out of the spirit of genetic algorithms and zero knowledge and all that stuff. But, I mean, why do you want a 50 length password, right? So I kind of implemented some stuff to force it there. And then you can kind of see here stuff that I had to implement as I went for various reasons, kind of related to IDS and IPS evasion. So you can pipe it through a proxy like Tor. Not that I know anything about that. You can pipe it through a list of proxies, give it some timeouts, delays. By default, it picks a random user agent kind of thing. And that's it. So let's see if I can run this thing. And let's see here. I'm going to go with like 50 threads, and I'll give each one 100 tries, which may not be great, but maybe enough. And I'll point this kind of to my local host. And a little caret just signifies where I want to inject. I'm using a self-signed cert, so I'm not going to check that. I know I forgot something here. Let's set the min to 5, max to 7, but I'm going to go ahead and run it, and it'll yell at me if I forgot something. Okay. So now here's the moment of truth, right? So every time it gets a hit, basically it spits out what its guess was and what the hit was. In this case, it's, there is no redirect or anything like that. There's no page title, so it just kind of spits out the same thing. And in a second here, it'll look like it's actually getting faster. It's not getting faster. What it's doing is it's having more hits per second, right? And so it's spitting out things faster and faster and faster and faster and faster. And, I'm doing 100 threads per, 100 tries per thread and 50 threads. So it'll take a while to finish, but hopefully if this goes like I'm expecting to, in a couple of minutes, it'll look like it's just zooming by. But in the meantime, let me just kind of show you the files it's generating. So here's kind of this database, discovered links SQLite, right? And this is just kind of a cache because you don't want to generate extra web requests. It just causes a lot of traffic and gets people angry at you. And it's also kind of fun if you run this thing for like 48 hours against one of these URL shortening services. You can just query this for like PWD equals, and you'd be amazed at the kind of things people kind of hide in those URL shortening services, which I recommend only hitting with appropriate permissions, of course, right? And then we've kind of got this upcoming generation.txt, which is basically a save file. And let's see what it's got there. So this is kind of what it's thinking, and in terms of next generation. And again, these are just kind of chances of picking certain things. So oddly enough, that you can see some length 7s here, and intuitively we know length 5 is better. This looks like it's doing all right. I kind of know the solution that it's going to wind up on. Sometimes it takes longer to get there, sometimes it's quick. So it's a little bit of a grab bag, but it does look like it's starting to zero in on some things. So here's 3 that have similar weights, and this will change periodically. And now before I show you the scores, let's just see if it's actually picking up some speed here. Okay, so now it's not getting real fast yet, but it's getting there, right? So this is a lot faster than the 1 per second kind of that we started seeing. So then the last file here that it generated is kind of score tracking. And that's exactly what it sounds like, right? So I'll show you what that is. So, okay, so it's at 3% with a kind of a maximum here of 10%. The best thread is 10% right now, which is still garbage. So we didn't get the best start in the world, but I promise you it'll get really good. But here's what's interesting, right? So here's where it started off with a raw brute force approach, and it was scoring less than 1%, right? So, I mean, we're talking pretty significant improvements. And the best performing thread, because I can't see it kind of this angle, is 2%. So we've gone from a 2% hit rate in what, like a minute of me kind of droning on. We went from a 2% hit rate to a, 10% hit rate. It might be even a little higher now. I can run it again. Yeah, now we're at 12%, right? So it's kind of like it's shooting off in the right direction, which is kind of cool. And you can see here it likes lowercase letters, and then it likes, it actually likes digits the most. It's zeroed in on these kind of length 5s and lower. And oddly enough, this is not what the statistical analysis showed, right? You're thinking, well, if you kind of take these million passwords, you get this thing that says statistically lowercase characters should be guessed more often, right? Which is weird, right? And if you look at it here now, it's going pretty quick, and it's got cached hits and all that stuff, right? So I'll just terminate this out and let it keep running. But here's where we kind of start getting to the really kind of cool part of this problem and why it's effective in these things. And that's kind of what it's thinking and what's going on here and why the hell is it having such a high hit rate. And if you guys couldn't kind of tell, I know the screen is small, kind of what returns the most hits is the direction it moves into, which is, intuitive and all that. And it's figuring out that numbers have, high return rate and shorter strings work better, right? Which makes sense. So if you were a person and you were trying to attack something like this, one of the first things you would do is you'd probably run a password dictionary, and then you'd run a bunch of numbers. right? So that's kind of interesting. Then again, this target is not a perfect simulation. For example, I'm not pulling things out as I go, so there's cached hits and all that stuff. Something kind of worth noting is it doesn't land on a pure solution very often, or maybe if it does, it takes a very long time. And even though it kind of zeroes in on going for numbers, it still makes guesses with letters. And I argue that's a really good thing in password cracking. And this is where it gets really cool, is that if I was doing this against passwords and I'm cracking them and pulling them out as I go, you kind of have this trait that when it starts exhausting the numbers, those threads start performing poorly, and the threads that are guessing more letters start performing better, right? So this thing will start pivoting. So it'll start guessing numbers, and then when numbers start performing poorly, it starts getting letters. And then after letters, who knows, it might have some kind of mix of the two, right? And, it is based on survival of the fittest, but there are some low-scoring populations that can kind of exist. So it still, kind of ties back to no pure solutions in that it can still guess, poor solutions periodically and kind of land wherever the heck it wants to, right? And then we've got mutation. I don't know if we saw any in there. I just kind of glanced at it. But mutation kind of keeps it from getting stuck at a certain point. So if it goes off in the wrong direction, periodically it'll make guesses off in all sorts of random areas, and sometimes they do pretty well, right? And, this example was something I built very specific to a very specific target and just kind of happened to work for a lot of things. But my character sets are fairly limited, right? You guys are probably wondering about things like, special characters, stuff like that. I didn't include them just because for my initial build or whatever, I didn't need to or didn't want to or whatever. But you guys can build this with any kind of character set you want if you want to take this kind of approach. Okay, so let's take a quick look at this now, right? And now you guys have seen it run, you know what all the caveats are, and I'll be blunt. This is not always the correct approach, right? This is not kind of a silver bullet that fits everything. It has some weaknesses, right? It needs a saturated target space because you don't know how well each thread is doing or how well each member of a population does unless you kind of have some way of measuring it, right? And if you're just hitting empty space, that's not so good, right? And then you've also got this kind of notion of password dictionaries, right? If you're doing an offline attack, I'm probably going to use a password dictionary 99% of the time first. And then if I've got the hardware for it, which I may have, right, I'm going to just brute force through everything like length 5 or lower. So this may not be the good thing, but maybe for an online solution or kind of if you don't have all the pieces, this might be a good fit. And oddly enough, it can come up with novel solutions, right? So guessing numbers is not something that a statistical approach would ever do. And so just statistic methods versus kind of machine learning is a popular debate, right? And there's people a lot smarter than me that know a lot more about everything here than I do, and they've been arguing this for a very long time, right? But the way I kind of see it is the bottom line is there's advantages both ways, right? So you can argue it till the cows come home. And I say that, kind of if you don't have the pieces and, there might be some kind of pattern, or maybe you have kind of some vendor that's doing what the one I was working with was, where they generate these tokens that are clearly designed a little bit wrong. This may be a good approach, right? This is kind of something fun. If you do have all the pieces, the tried and true may be the best way to go. And that's just kind of how it boils down. But, even when it doesn't work, something like this is pretty fun to just kind of fire off at, a URL shortening service and kind of just see what it comes up with, right? So I'm just going to talk about it briefly. And most of that's because I can't go too in-depth onto it. But we'll talk just real quick another machine learning approach in offensive security. And this is nothing new. People have been doing this one for a while, actually. And what I did was I kind of, there's some existing software. It was put together by a guy, Andres Karpathy, to give credit where credit is due, right? And he basically said I can use a neural network to create characters, and he wrote a paper on it. Basically, a neural network is this kind of thing that's designed to imitate your brain and the neurons and how they work. And you feed data into an input layer. It has some processing layers and it spits out an output, right? But it can have this kind of cool property in that you can train it on some data sets and it'll spit out, similar kind of data sets. And so in his paper, he kind of talked about how he could use it to feed a bunch of Shakespeare and print out Shakespeare, or feed a bunch of music and spit out similar music. And, you know, I see all these beautiful kind of artistic uses for this thing, and I say, boy, I bet I could cram that thing full of passwords, right? So I did. And other people have probably done this too, right? But in this case, I just took eHarmony cracked passwords, which, you know, are all uppercase, just kind of by the nature of the hash, I think. And, or that's how I guessed them. And fed it through a bunch of times. And then these are all kind of things that the machine generated, right? And you can go out, get this software, download it, tinker with it. And you can see some of these are actually like, you know, they look like real passwords. So Rocky Baby 00, that's somebody's password, right? Some of these are less real passwords, like Land Arena. You can kind of see where it was going with it, but it's maybe doesn't make so much sense. Or I love Minimont. I don't know what that means, right? There's some kind of funny stuff there. I actually had to censor this because I didn't expect it to do it, but it spat out a lot of bad language, right? I guess people use those as passwords for some reason. But, you know, you can kind of see where this application goes. So, dictionary creation. You take a million good dictionaries, you feed them into this thing, and you can spit out kind of, you know, other good dictionaries, hopefully. There's also dictionary expansion. So, the other day I get into a database and I get 12,000 unique clear text passwords, right? And that turns out to be a great dictionary for me. So I can feed it through a tool like this, and I can turn it from 12,000 unique passwords to 25,000, or however many I need, right? And, you know, full disclosure, I've actually used this before a couple of times, and sometimes it's good, most of the time it's not. It's kind of a niche situation, right? The thing I have used it for is after you've kind of done all your cracking and you've gone through all the password rules and all that, and you're starting to hit this bare bones, and there's like, you know, some small percentage of hashes left. You can kind of take the hashes that were successfully cracked, pipe them through this thing, and maybe get a couple other hashes to kind of jumpstart yourself again, right? So that's kind of where this has uses, but I think it's darn cool, so it made it into a slide, right? I just realized I'm talking ridiculously fast, but that's okay, right? So we're next with something like this. Well, the thing that I kind of mentioned, right, is you can change character sets. So there's no reason that this tool has to be limited to kind of the character sets that I built in. You could take it to a very, very granular level where you do individual characters. You could look at pairings. So, you know, H comes after T a lot, U comes after Q, and all sorts of things. It's already written in Java, so I'll probably build it into a Burp Suite plugin some point in time, right? I use it once in a while. I use Burp Suite every day. It'd be kind of cool if those two things worked together. And it's not a huge jump for me to integrate it into something like that. It's just a question of me being really lazy, right? It's my perpetual downfall. And then kind of, you know, I kind of want to take this to the next level. So you don't see genetic algorithms kind of working by themselves, you know, terribly often. They're often paired with kind of other algorithms. So it would be kind of cool if I did that and gave it access to not just character sets, but, you know, dictionaries and rule sets and Hashcat, and kind of just had this hash cracking automated from start to finish for me, right? Or I think that'd be cool. And so let me get to the bottom line, right? And here's kind of my closing thoughts. And that is, it works. And in some cases, it can actually work surprisingly well, right? It's even when it doesn't work, it's kind of fun to watch this thing go off and do some kind of oddities. And if anybody cares, all my source code's up there on GitHub. I kind of threw it up there. I also threw some kind of data exfiltration tool up if anybody is interested in that. And, you know, the big thing that I want you guys to take away is that machine learning has offensive applications, right? So, you know, hopefully somebody will go out there and build the next Skynet that I can leverage, and that'd be kind of useful, right? So that's, like I said, I apologize. I got a little nervous, talked a little fast. So, questions? Go for it.
Which kind of hash types you can reinforce with your application?
My application is not so much for hash cracking. It's for online type attacks, right? But if you wanted to apply something like this to hash cracking, you would be able to implement it for whatever one you wanted, right? Or you could let some other tool implement the hash algorithms for you, like Hashcat, and you could code your parameter set, which is basically what the genetic algorithm is guessing as inputs to the tool, Hashcat or something like that. Well, yeah, so I mean, the cool thing about this is you don't program rules, it kind of comes up with them itself, but you can actually you can put that behavior into it if you want to using a proxy, right? So kind of back here on the tool, it supports proxying and things like that. It also has this save file, which is upcoming generations, and you can modify that however you want. So you can kind of set it with things that you know to be true ahead of time. But one of the advantages of something like this is that it can explore possibilities that you may not explore yourself, right? So giving it maybe a broad base and then kind of letting it kind of shift and pick its own direction may be the advantage of something like this. But you could do that. It's Java, and I didn't use any of these fancy OS-specific stuff, so it should probably work on everything. I think I've used it on Windows and Mac, mostly Mac. But it should just be fire and go. Java 1.7 probably. I don't use 1.8 much.
Have you tried this for like directory filing brute forcing and compared that to like
Okay, so I mean, I haven't in this particular case tried that for dir busting. That's kind of an interesting idea. I think that if I were to do something like that, I'd want more granular character sets, right? I'd want it to know individual letters and likelihood, and I'd want it to look at previous letters and things like that. And the reason I do that is just because right now it's designed to brute force things like passwords. And for those, my primary concern is what character set I'm going to choose from, right? But that's kind of an interesting application, and I'd be curious to see how that would work. If you have kind of unlimited resources, you know, dir busting with a massive file list is probably fine too. Yeah.
is your approach to say train the algorithm until it finds like a pattern that's decent and then just run that pattern into the ground? Or do you leave it as sort of continuously train itself?
Yeah. So it depends on what I'm doing. A lot of the time, I just kind of run it until I see something that's around a percent that I like, and then I take it and just, you know, duplicate that in Burp Suite or something like that and just fire it off, right? Because there's a certain point where it's just good enough, but, you know, once again, you could do it the other way too and just leave it running overnight, and sometimes it'll kind of deviate, so it kind of does this, right, in terms of how good its solution is. Sometimes it's better, sometimes it's a little worse, so I don't know. Yeah. Yeah, okay. So that's a good question. And the short answer is I don't know enough about Markov chains to give you a appropriate answer. I know that they're implemented in Hashcat, and they're decent. I probably should have done that on the little graph, but I did not. So sorry about that. Yeah. 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 So this is the graph back here. Yeah, this is against my target, which is 44 million real-world passwords and probably a language dictionary thrown in there. And then again, the caveats here, and I did 10,000 runs per thing, right? So 10,000 for my algorithm. I did pretty much what this gentleman said, where I ran it a couple times, picked a good thread, and then did that, right? But yeah, this is 10,000 runs, length 6 against 44 million passwords. Yep. All right. Well, thank you guys. It's been fun.